Alright, I'm ready to show you some things with integrals. The first section is 5.1, areas and distances. So I wanted to start off showing you calc in motion to get kind of the big picture before I do a couple of examples. So let me show you this. Okay, so let's say I want to try to find the area under this curve. I could use these little rectangles, and you can see I've chosen just two rectangles. Oh, nice. Okay, I'll pause that. And then if I increase the number of rectangles, that will actually be way more accurate. So you see 3. It starts getting a lot more accurate as far as describing the area under the curve. The more rectangles, it looks like way better, more accurate. Because when I don't have as many rectangles, there's a lot of overhang, off the curve. And it looks like as we increase the number of rectangles, we're getting a lot more accurate as far as the true area under the curve. That's a left sum right there that we'll talk about. And then if I change it, if I hide that, then I can do a right, and I'll kind of explain what that means in a second. And again, pretty accurate when you have that many rectangles. If I stopped it and I went back to just barely any, like 2 rectangles, it's just not very accurate at all. Look at all that's overlapping right there. And then all this that's underneath it, so it's just not as accurate. So we just want a lot more rectangles. The more, the better. Okay, so back to the examples. Okay, let's say we want to estimate the area under this parabola from 0 to 1, and the curve is y equals x squared. What we could do is we could, pretend like we could just do a triangle. We could just make a triangle here. And we can say, okay, the area of the triangle, 1/2 base times height. And we can see the base of the triangle is just 1 unit. Oops, forgot the 1/2 in there. So we got that equals 1/2 times 1, and then the height, of course, is 1 as well. So we get area equals 1/2. Well, we know that that's not very accurate because it doesn't, we're pretending like it has all of this and it doesn't. So, but at least we know that our area is somewhere in between 0 and 1/2. Would you agree? It's got to be somewhere in between there. Okay, let's try to use some of our estimates here. Now, when you want to set up your little strips or your rectangles, the way that you do it is if you want to find the area between A and B, let's say that's your interval, you want to find your interval width, and that's going to depend on however many rectangles or how many strips you decide to use. And if you want to figure out the width, what you do is you just subtract, the B minus the A, and then divide by however many strips you want to do. Again, pretty much rectangles, we could say. So B minus A, in our case, we're going to do 0 to 1, and so that would be 1 minus 0 divided by, I'm going to do 4 strips, so that means that each of the interval widths would be 1/4, and so you see my picture here makes sense from 0 to 1. You guys would all agree that each of the strips would have to be 1/4 if you're splitting up 1 into 4 parts. Okay. So what I'm going to do is I'm going to try to find the right endpoint. And what that means is that I'm going to pretend like my little rectangles are as tall as the right side of the interval. So this right here, let me go ahead and write my intervals. So my intervals are 0 to 1/4. My next interval is 1/4 to 1/2. And then my next interval is 1/2 to 3/4. And then my next interval is 3/4 to 1. When we say that we're doing a right endpoint, we're saying that we're pretending like our rectangle is as tall, it has the height of whatever the right endpoint is of each of the intervals. So each of these, we're pretending like the rectangle is that tall, and we're going to use that to find the area. So visually what we're saying is from 0 to 1/4 right here, I'm going to pretend like my rectangle is actually this tall, when in actuality it's not, right? It seems like it's already over what it's supposed to be. But I'm going to draw a rectangle, and that's going to be the height of it. Then when I go to my next interval, I'm going to pretend like my rectangle is as tall as the right side of that interval, so I would sketch my rectangle that tall, like that. Then I would go to my next interval from 1/2 to 3/4, and I'm going to pretend like my rectangle is this tall. So I'm going to draw it. There's my third rectangle. Then I'm going to go to my fourth rectangle. I'm going to pretend like it's as tall as the right side of the interval. So it's going to be like that. And then I'm going to kind of shade that in. So I've got 4 nice rectangles there. All I need to do is find the area of each of those rectangles and add them up. And that's going to give me an estimate for the area under the curve. So I would take the interval width. It's always going to be the interval width. So it's going to be 1/4 in this case. We figured out right here. So 1/4. And then it's going to be times however tall this thing is. So if you have a function, you're going to take the x values, that are right here, and you're going to plug them into the function to see how tall it is. So in this case, I would do 1/4 and square it, because that's what my function is to get the y-coordinate. So that would be 1/4, and then of course I would square it. And then I go to my next interval, and it looks like 1/2. And I have to multiply it by 1/4 each time, because that's the width of my little rectangle. And then it's going to be 1/2, and then I square it. And then I would do the next one, and that has a right endpoint of 3/4, so I do my interval width to 1/4, and then times 3/4, and I square it. And then plus my interval width of 1/4, and then I have my right endpoint here of 1, so then I have 1 squared. If I add all those up, that's just adding up the areas of each of those rectangles, and that would be the total, area, which again is an estimate. So when I did all of this, I know you guys can do the fraction work. The first one, I'll just show the work. It's 1/64. The next one is 1/16. The next one was 9/64. Assuming this one, right? Okay. And then the next one is 1/4. And if you get a decimal approximation, decimal approximation for this is 0.4685. Okay. Now, is that an overestimate or an underestimate? Well, geez, I hope we say it's an overestimate. Okay. So this is an overestimate. And that's going to happen. It's not that the right is always an overestimate, but it is when it's an increasing function like this. Okay, because the function's going up, and so if you do the right endpoint, you're gonna always end up being an overestimate or getting an overestimate. All right, let's do the same thing, but let's do the left endpoints. So now what we would be doing is we would pretend like our rectangle is not as tall as the right side of the intervals, but it would be as tall as the left side of the intervals. So I'm going to just write my intervals again. Okay, so as tall as my left ones are these. So these would be the ones that I would plug into the function to get the heights. And other than that, it's exactly the same. So this would be L sub 4. The interval width is 1/4. And I would plug in the 0. See, and now I'll do the visual first, so it makes more sense. So now I'm pretending like my rectangle is this tall, which is not any rectangle at all right there. And then the next interval, I would pretend like it was this tall. So it'd be like this. There. And then the next one would be this tall, like that. And then the fourth one would be only this tall. And you can already tell, you're like, dang, that's going to be an underestimate, when we calculate this. So I hope you see that. I know you do. So then we're going to do this, 1/4. I'm supposed to square this. And then 1/4, and then to use the left, it would be 1/4. Squared plus 1/4, and then 1/2 squared. Then the left endpoints, and then plus 1/4 interval width, and then times 3/4 squared. And save us the fraction work. I know that you can do that, and it would be 0.21. Yeah, that's ugly too. 0.2187. Oh, come on, dude. 21875. Okay, so that's what we got. So we know that this is definitely an underestimate. Okay. So what we can do is we could average the two, because we know that the right answer is somewhere in between there. Underestimate. Okay. So we know that our actual area is right in between those two. So point maybe let me write it. Let's see. Yeah, there we go. 0.21875 you said, and it has to be less than 0.46 because we had all these rectangles that were above it. Okay, so the area is in between there. So good. We could average the two. If we add them up, divide by 2, we average them, and we would get A is approximately 0.34375. You guys okay with the averaging process? Okay, add them up, divide by 2. All right, you can also use the midpoint. So you could have those same intervals. And let's write the interval once more. Okay. Good. So now what we're going to do is I'm going to pretend like the rectangles are as tall as the middle. And so I would pretend like the heights of the rectangles are this tall. So then I would sketch that. And so in between, in the middle, I'd pretend like the rectangles were that tall. And then in the middle of the interval, so about that tall. And I don't know if you can see that part of it is under and part of it's over. And you're thinking, this could be pretty good. Yeah, that's pretty good. So the midpoint is actually always more accurate than the left and the right. So for the midpoint, when I did the calculations, I did 1/4, and then the middle of the interval from 0 to 1/4 is 1/8. Okay. So I won't show you all of these because I know you can do this, but the middle right here, will be 1/8. Well, and then 3/8, and then 5/8, and then 7/8. Maybe I will show you all of them. Okay. The other shortcut you can kind of do on this is if you know you're going to multiply by 1/4, you can just put it on the outside of the brackets, and just put your heights here. So 1/8, and then you do have to square it, and then plus, just because we don't always square it, right? It depends on our function. All right, and then 5/8, and then to get the height of this one, we do 7/8 and square it. All right, cool deal. Well, when I did the midpoint, I got 0.3282125. So check those out. You make sure I did the calculations right. So that's pretty cool. Well, I wonder what the exact area is under the curve from 0 to 1 for this function. Well, do you remember antiderivatives? Well, it's a little bit early for this, but this is an integral. This is an integral notation. An integral is the exact, net area under the curve. So the area of this, you would just find the antiderivative of that function. And so we would add 1 and then divide by it. And then we actually evaluate it from 1 to 0. So I'm going to go ahead and just do that. And so then we plug in the 1 into this. We'll plug in the 1 wherever there are x's. So that would be 1/3. And then you always have a minus, and then you plug in the 0 in for that. So then you get 0. No worries about this. We'll teach this later. but we get 1/3, which is the exact area under the curve from 0 to 1, because that's what an integral is. So very cool. All right, we were pretty close with the midpoint there, 0.32. It's pretty good. All right, we're almost there. I've got a little bit more. Let me see how I'm doing time. 15. Okay, I'm trying to finish up in 5 minutes. Okay. So the area of the region S that lies under the graph of the continuous function is the limit of the sum of the areas of approximating rectangles. What this basically means is that if you want to find the area under the curve, it's going to be equal to letting your number of rectangles just go to infinity. I mean, you know, if you had a whole bunch of rectangles you saw from the calc in motion, we start getting really accurate. And so if we say that the limit as the number of rectangles goes to infinity, we're going to just say that that equals the area under the curve. And later we're going to go ahead and just say, you know what, that's what an integral is. That's what we'll say in the very next section. So we can already say that now. And so these are the same thing, the blue and the red. The only thing that's different is you can see the notation's different, that the right endpoint is using the very last, the very right side, so it's the very last, what would you call it, your last strip. And then the left is using the endpoint right before, right before the last, the endpoint, not the right endpoint, but the left endpoint of the last strip. So it's just kind of a notation thing, so no worries on that. I can show you that in classic, but it doesn't make any sense. All right. Here's the last thing. It's an application. We're going to do our Chapter 5 project is this exact same thing. So we have an odometer that's broken. That's the thing that tells how many miles you drive. And we want to estimate the distance traveled over a 30-second interval. And every 5 seconds, we looked at the speedometer and we saw, the velocity, which is speed if it's always going to be positive. So at 0 time, boom, it was 25 feet per second. Well, we have a weird speedometer because it's just feet per second, but that's all right. So 5 seconds, 31. So this is what the little speedometer showed. Okay. Well, what we want to do is we want to go ahead and estimate the distance that we traveled. So after you jot that down, we would make a graph. We don't have to make a graph. I mean, you will for your project, but you can solve this without making a graph. But I went ahead and I plotted the points. And then what I'm going to do is I'm going to go ahead and I'm going to try to figure out the distance that we traveled. Now this is really cool because if you kind of think about this, I think I'll just draw one with the right endpoints first. If I made a rectangle like this, look at what the area of the rectangle is. The rectangle is, if I want to find the area, the rectangle is time, which is what this is. This is time. So if I take time and I multiply it, take time and I multiply it by this length, which is what? Velocity. When you multiply those two together, you actually get distance. Okay? So, approximation here, we're going to take our time and our velocity, and we're going to get distance. And so, first one I'll do, let's see, I'll do a left first. And I'm going to do how many strips? 1, 2, 3, 4, 5, 6 strips, I believe. Yeah. So I'll do L sub 6. And so I've got 5, they're 5-second intervals, right? So I'm going to do 5, and I'm going to just try to save a little space. I'm going to put the 5 on the outside. And then I'm just going to pretend, again, this time I'm going to do the left one first, so I lied. So I'm going to pretend like the rectangles are as tall as the left interval. And so they'd be this tall. Okay? And then they'd be that tall. You get the idea. You don't have to graph this. I'm just doing a visual on it, so it makes a little bit of sense. So the left side of each of these intervals. So the first one is 25, and then the next one is 31. And I'm going to end up using all the values in the data table, except when I'm doing the left, I don't use the last one on the right. So I have 31 plus 35 plus 43. 43, wow, that's a 43. And then 47, and then 46. Okay, that's in brackets. It's ugly. It's in brackets. And that gave me an estimate of 1135 feet. And let me kind of show you the units here. So if we multiply, let's see, the width was feet, and then we were multiplying by feet per, what were we multiplying by? Feet per second. Then, oh, I was totally joking about that. We're multiplying by time, so that's seconds. And we're multiplying by feet per second, so it makes sense. We multiply those, that our units turn out to be feet. Okay? And then we could do the same thing if we just do a right estimate. So we do R6, and you get the idea, hopefully. You multiply by 5, and then now you're going to pretend like your rectangles are as tall as the right side of each of the intervals. So we basically would use all of the data points except for the first one. So we would start at 5 seconds, not 5 seconds, 5 feet per second. Oh, I'm sorry, I'm thinking about my kids that I need to pick up. Let me erase this. Okay. So we would start with 31, thank you. And then we would go to the next one, 35, and this darn thing is not working. And then 47, and then we would do 46. And then we would use the right endpoint this time, so 41. All right. So when I did this, I got an approximate. It is an approximation. It's going to be 1215 feet. All right. So that's gonna do it for us. Thank you.